GCE Advanced Level Chemistry Practical Series Experiment number 27, Tests for Aldehydes and Ketones. And in this practical, we will be focusing on observing the characteristic reactions involving aldehydes and ketones. Let's move on to identifying the reagents we will be using for this practical. These are the reagents we will be using for this practical. We will be using methanol, also known as formaldehyde, ethanol, known as acetaldehyde, 2-propanone, also known as acetone, and we will be using benzaldehyde, acetophenone, and methanol. To test these things, we will be using reagents such as 2,4-DNP, which is known as 2,4-dinitrophenyl hydrazine, 2,4-dinitrophenyl hydrazine. It is commonly known as Brady's reagent as well. We have our potassium permanganate, KMnO4, potassium dichromate, K2Cr2O7, which is orange in color. Potassium permanganate is purple in color. I'm pretty sure by now you are familiar with these colors. We have tolerance reagent. What we have here as tolerance reagent is ammoniacal silver nitrate. So make note of that as well. We have our failing solution, a solution made with two components, which is failings A and failings B. More information about that will be delivered to you when we are doing the experiment using failings reagent. Apart from that, we will be using some test tubes, a wash bottle, and a few droppers as well. Let's move on to our first experiment, solubility of these aldehydes and ketones in water. To see the solubility of water of these aldehydes and ketones that you have over here, we will be taking each of these aldehydes and ketones, or we can call them carbonyl compounds, and we will dissolve small amounts of them in a little bit of water. If you do not see a layer separation, that means it is soluble in water. Once you observe two layers being formed, that indicates that that particular aldehyde or ketone is not soluble in water. Let's take a small test tube and let's take formaldehyde or methanol and transfer small amount of methanol into a test tube. So now we have taken small amount of methanol into a test tube like this. You can see the colorless layer over here is our organic layer, which is the methanol layer. Now to this, we will add a little bit of water to see if this methanol is soluble in water. We have our wash bottle containing distilled water. So let's add small amount of water to see if it is soluble in water. As you can see, upon addition of water, we do not see two layers forming here, which means that methanol was completely miscible in water, or it is soluble in water. So you only see a single layer. You do not see formation of two layers, indicating that methanol is soluble in water. Now let's move on to ethanol or acetaldehyde. So you have here your ethanol reagent. We will take small amount of ethanol into a test tube. We can see a clear layer over here that is containing ethanol. And like in the previous experiment, we will add a little bit of water to see if ethanol is soluble in water. You can see after addition of water and after I shake it a little bit, after I shake the test tube a little bit, you do not see formation of two layers indicating ethanol is soluble in water. Does this mean all the aldehydes are soluble in water? Not necessarily. Not all the aldehydes are soluble in water. Aldehydes with shorter carbon chains are soluble in water, whereas aldehydes containing lengthier carbon chains or long carbon chains are insoluble in water. The reason for this is when a carbon chain is extremely long or considerably long, that entire aldehyde molecule will become nonpolar. So this nonpolar nature of those aldehydes will not allow those aldehyde molecules to dissolve in a polar solvent like water very well. So that is why we see short chains aldehydes like methanol and ethanol dissolving well in water. Let's move on to a ketone. So we have here 2-propanone. Now 2-propanone is commonly referred to as acetone. I'm pretty sure that most of you are very familiar with acetone. So we will take our 2-propanone and let's see if it is soluble in water. We'll take a test tube and transfer a small amount of propanone or 2-propanone into a test tube and add small amount of water with the help of our wash bottle. Here you can see on addition of water into 2-propanone, we did not form two separate layers, indicating that 2-propanone or acetone is soluble in water or miscible in water. So does that mean all the ketones are soluble in water? Again, not necessarily. Short chain ketones are soluble in water just like in aldehydes, and when the carbon chain is longer, the ketones will become insoluble in water. Keeping that in mind, let's move on to an aromatic aldehyde, benzaldehyde. We have here an aromatic aldehyde, which is benzaldehyde. Let's see if that is soluble in water. We'll take a test tube and we will add benzaldehyde into this test tube. We'll take a small quantity like this of benzaldehyde. Now to this, let's add a little bit of water. You can see when water is added, we can very clearly see formation of two layers. At the bottom of this test tube, we have our benzaldehyde. It's high in density, so it has sunk to the bottom. And over on the top of this particular test tube, we can see a layer of water present. So this indicates, now if I give it a little shake, you can see we can try to dissolve it, but if you leave it for a while, we can see the tiny droplets that are formed due to shaking of this test tube again sink to the bottom. Tiny droplets of benzaldehyde that is formed actually sink to the bottom and are separate into two layers as before. So this indicates that the benzaldehyde that we have here is insoluble in water. It is mainly nonpolar in nature, so it does not necessarily dissolve well in water. So you can see the formation of two layers. Let's take a look at acetophenone, which is an aromatic ketone. So we will take a little bit of this aromatic ketone into a test tube. You can see acetophenone present here. Then we'll add a little bit of water to this. You can see when we add water, acetophenone remains at the bottom as a separate layer and water is present on top as a separate layer. So water and acetophenone are now present as two separate layers, indicating that acetophenone does not dissolve in water. Even if you shake it, you can see acetophenone droplets are formed, but after shaking for a while, acetophenone will sink to the bottom due to its high density and separate out as two layers. Right? So this indicates very clearly acetophenone is not soluble in water. So to summarize, we saw that when we are dissolving aldehydes and ketones, aldehydes or ketones that contain short carbon chains actually dissolve well in water. However, if we are moving on to aromatic aldehydes or aromatic ketones, or aldehydes or ketones with lengthier carbon chains, we saw that those are not soluble in water. So we have here formaldehyde was soluble in water. You do not see a layer separation there. Then we had acetaldehyde or ethanol, which is soluble in water. You do not see a layer separation there. We have acetone or 2-propanone, soluble in water, did not form two separate layers. We have benzaldehyde, which was not soluble in water, so two separate layers were formed. Finally, we have our acetophenone, again was not soluble in water, so therefore two separate layers were formed. Now let's move on to reacting these aldehydes and ketones with 2,4-DNP. We are going to test how the aldehydes and ketones react with 2,4-DNP, 2,4-dinitrophenyl hydrazine, or commonly known as Brady's reagent. So over here we have two aliphatic compounds and two aromatic compounds. What we have here is an aliphatic aldehyde, an aliphatic ketone, and then we have an aromatic aldehyde and aromatic ketone. So we are going to see how aliphatic carbonyl compounds and aromatic carbonic compounds react with 2,4-DNP. So let's take a test tube and take our 2,4-DNP reagent so that you will be able to observe the color of 2,4-DNP. We'll take a small amount of 2,4-DNP. To our test tube here. So we have our 2,4-DNP solution over here. We can see a characteristic orange-yellow color. So to a different test tube, we will take our aliphatic aldehyde, which is acetaldehyde, or in other words known as ethanol. We'll take a small amount of ethanol into this test tube. To this we'll add a little bit of water to make aqueous solution of ethanol. And to this, we will add our 2,4-DNP solution. Please note the observations when I mix these two. As you can see, as soon as 2,4-DNP is added to this aqueous ethanol solution, we started forming a yellow-orange precipitate. So this yellow-orange precipitate is the positive answer to 2,4-DNP test. You can see the 2,4-DNP has a different color to this, and as soon as 2,4-DNP is added onto our ethanol solution here, you can see the formation of a yellow color precipitate. Let's give it a little mix. Now you can see the 2,4-DNP, upon addition of 2,4-DNP, a precipitate is formed which is yellow-orange in color. This is a positive answer to our 2,4-DNP test, indicating we have a carbonyl compound here. Let's move on to 2-propanone. Let's take a new test tube and we'll take our 2-propanone here, and to this test tube we will add small amount of acetone or 2-propanone, and we'll add a little bit of water into this. Now we have our mixture with acetone and water. To this, we will add our 2,4-DNP solution. You can see, upon addition of 2,4-DNP, a yellow-orange color precipitate formed. Different types of aldehydes and ketones form slightly differently shaded precipitates here. So you can see these two precipitates are not the same color. We will add a little bit of 2,4-DNP to increase the color that you see here, but you can see the two precipitates that you form are not the same color. They vary in color from yellow-orange to sometimes even yellow-red color. So we saw that acetaldehyde and acetone both answered positively to the test with 2,4-DNP. So those are all aliphatic compounds. Let's move on to our aromatic compounds. Before that, we need a little bit more 2,4-DNP. So we'll take some more 2,4-DNP into a test tube. We have taken another additional amount of 2,4-DNP into a separate test tube to react with our aromatic carbonyl compounds. And we will now take one of our aromatic aldehydes that we have here, which is benzaldehyde. We'll take a small amount of benzaldehyde into a new test tube. Now I have taken a small amount of benzaldehyde into our test tube. So as you saw earlier, benzaldehyde does not mix well with water. So what we can do to carry out this experiment is to introduce a co-solvent, a solvent that dissolves both in benzaldehyde as well as in water. So we will be taking methanol as our co-solvent. That is what our textbook suggests. So we will take methanol as our co-solvent, and we will add small amount of methanol into this test tube. Now, as you can see, when I added methanol into this test tube, it mixed well with the benzaldehyde that was there in this test tube. So methanol and benzaldehyde mix well with each other. Now I'll be adding Brady's reagent into this mixture. So we have our Brady's reagent here. Let's add small amount of Brady's reagent into our mixture here. As you can see, as soon as we add Brady's reagent, the color starts to change. So this color change indicates the presence of a carbonyl compound. So when I add a little bit of water, you can see the color change a bit more clearly. So you can see a precipitate that has formed. At the bottom, you can see the formed precipitate. A yellow-orange precipitate is formed. This is indicative of the fact that benzaldehyde is indeed a carbonyl compound that reacts with Brady's reagent. Let's take a look at an aromatic ketone. We have here acetophenone, which is an aromatic ketone. So we'll take a small amount of acetophenone into a test tube. And to this acetophenone, we will add a little bit of methanol, right? Like in the previous experiment with benzaldehyde, we have to add methanol to make sure that this acetophenol dissolves well with the 2,4-DNP. So we will add a small amount of methanol. And now, to this methanol acetophenone mixture, let's add our 2,4-DNP. You can see upon addition of 2,4-DNP, the color of the solution changed. We'll have to add a little bit of water to see this clearly. So we'll add a little bit of water here. Now we can see the formation of the yellow-orange color precipitate very clearly. At the bottom you can see that it's starting to accumulate there as well. So acetophenone, in the presence of 2,4-DNP, will be forming a yellow-orange precipitate as well. So let's move on to our summary. So as you know, 2,4-DNP, 2,4-dinitrophenylhydrazine, is used to identify carbonyl compounds. Regardless of whether the carbonyl compound is aliphatic or aromatic, it will answer to the 2,4-DNP test. The positive answer to the 2,4-DNP test will be the formation of a yellow-orange precipitate. As you can see, when we reacted acetaldehyde, a yellow-orange precipitate was formed. You can see by the cloudy nature of this solution over here that this is due to formation of tiny, fine particles of precipitate that turns the entire aqueous medium into a yellow-orange suspension. And then we reacted acetone with 2,4-DNP. You can see again a cloudy precipitate is formed here due to the reaction of acetone with 2,4-DNP. Now, when you are forming different types of precipitates here with 2,4-DNP, you can see the colors that are present are different. They will not all be the same color. Depending on the aldehyde or the ketone that you're using, the color of the precipitate may slightly vary. And then we took an aromatic aldehyde, benzaldehyde. You can see upon addition of 2,4-DNP, benzaldehyde started forming a yellow-orange color precipitate. Now this precipitate is more towards the orange color. And then upon addition of 2,4-DNP to acetophenone, it also formed an orange or yellow-orange color precipitate, as you can see here. So finally, you have to make the observation that upon addition of 2,4-DNP, all the aldehydes and ketones will answer positively as long as we are reacting 2,4-DNP with the carbonyl compounds, all the carbonyl compounds, regardless of whether they are aliphatic or aromatic, will answer positively to the 2,4-DNP test. Let's move on to the reactions of aldehydes and ketones that you see with potassium dichromate. In this section of the practical, we are going to see how aldehydes and ketones react with acidified potassium permanganate. Here we have our acidified potassium permanganate solution. Like in our previous experiment, we have two aliphatic compounds and two aromatic compounds. For our aliphatic aldehyde, we have acetaldehyde and we have acetone as our aliphatic ketone. For our aromatic aldehyde, we have benzaldehyde over here, and for our aromatic ketone, we have acetophenone. So now we'll move on to our aliphatic aldehyde and ketone. First of all, we'll take a small amount of our aliphatic aldehyde into a test tube labeled A. Into this test tube, let's add a small amount of our aldehyde, which is acetaldehyde or ethanol. We only need to take a small amount. And to this, we will add acidified potassium permanganate. This potassium permanganate is acidified. As you can see, upon addition of acidified potassium permanganate, very quickly the solution is turning colorless. So, in the presence of ethanol or acetaldehyde, you can see acidified potassium permanganate got decolorized. What happened there? What happens here is, since acidified potassium permanganate is a good oxidizing agent, the acetaldehyde that we used or ethanol that we used got oxidized to ethanoic acid. So the ethanol that we used got oxidized to ethanoic acid. Now let's move on to our aliphatic ketone. For our aliphatic ketone, we have 2-propanone, or commonly known as acetone. So let's take our test tube that is labeled B. So to this test tube that is labeled B, I will be adding a little bit of our acetone reagent we have here. As you can see, I have taken small amount of acetone here. To this, I will be adding acidified potassium permanganate. So we have our acidified potassium permanganate here. And now I'll be adding acidified potassium permanganate into our acetone that we have here in our test tube. So unlike in the previous example, when I added acidified potassium permanganate into acetaldehyde we have here, we saw potassium permanganate got decolorized. But here we still see the color of potassium permanganate. This could be due to two reasons. It could be that acetone does not react with potassium permanganate, or the reaction is slow at room temperature. You do not see a drastic color change. So to avoid having a doubt about that, we will heat this reaction mixture up to see if this reaction takes place at a higher temperature. So if it does not decolorize at that point, we can be sure that in the presence of acidified potassium permanganate, there will be no reaction with acetone. So to avoid having any doubts, we will now give this mixture some heat through a water bath. I will place this test tube labeled B on a water bath, and to make sure that we have a controlled reaction, I will take a small amount of acidified potassium permanganate into another test tube, and now this test tube is not labeled. I'm going to place this control test tube on the water bath as well to see if there's any color change that is happening when you heat potassium permanganate. So let's include this test tube as well in our water bath. Students, it has been a while now. I have allowed it to heat up for a while. Now let's see what has happened after we provided it some heat. So we have here our two mixtures. So we have the test tube labeled B, which had potassium permanganate, acidified potassium permanganate and acetone. And on the other beaker on my left hand, we have our potassium permanganate solution that is acidified. So upon heating these two, we saw that no reaction took place, that the color of acidified potassium permanganate did not change, as well as when we try to react acidified potassium permanganate with acetone, we saw that there is no color change. The reason for this is you cannot oxidize aliphatic ketones with the use of acidified potassium permanganate. Although acidified potassium permanganate is a good oxidizing agent, you cannot oxidize aliphatic ketones with the use of acidified potassium permanganate. Now, let's move on to our aromatic carbonyl compounds. We have two aromatic carbonyl compounds here. We'll first take a look at our aromatic aldehyde, which is benzaldehyde. So we have our benzaldehyde reagent here. We will take small amount of benzaldehyde and transfer small amount of it to our test tube that is labeled A. I'm going to be transferring a small amount of benzaldehyde to a test tube labeled A. And To another test tube labeled B, I will be transferring our aromatic ketone. So we have acetophenone as our aromatic ketone. So I'm going to take a small amount of acetophenone and transfer it to this test tube labeled B. Aromatic aldehyde and ketones are not soluble in water, so therefore we are going to be using a co-solvent, which is acetone, before adding potassium permanganate. So let's take acetone or 2-propanone, which we know will not answer to potassium permanganate. So we will be using acetone as a co-solvent because we know that it is not anyway answering to the test that we do with acidified potassium permanganate. So we can use acetone as a co-solvent. Now in our test tube A, we have benzaldehyde. In our test tube B, we have acetophenone. So to each of these test tubes, let's add acidified potassium permanganate. So we have here acidified potassium permanganate. Now we will add small amounts of acidified potassium permanganate into each of these test tubes. You may observe upon addition of acidified potassium permanganate, there is a slight decoloration of the acidified potassium permanganate layer, as well as that they are organized in two layers, right? In both tube A and tube B. That means when you add acidified potassium permanganate to benzaldehyde, you can see over here, the acidified potassium permanganate is starting to lose its color, but this is a very slow reaction. And even when you add acidified potassium permanganate to acetophenone, which is in our tube B, you will see the color has started to decolorize. So now, to expedite this reaction, to make it happen a little faster, let's place both of these test tubes on a water bath. So let's place them on a water bath like so. But before we do, let me give it a little mix. And then let's place, now you can see upon mixing them well, the color of the acidified potassium permanganate almost disappeared, but there's still a persistent color here. But let's place them in a water bath to see if we can get them to be completely colorless. Students, we have allowed the two test tubes to heat up in a water bath for a while now. Let's take them out to see the observations. So in both of these test tubes, we no longer see the color of acidified potassium permanganate. So we do not see the purple color that we saw earlier after we heated them for a while. We still can see a layer separation in both of the test tubes. However, we do not see the purple color. This is because acidified potassium permanganate has oxidized the aromatic aldehyde and the ketone into carboxylic acid, and in doing so, potassium permanganate or permanganate ions have reduced to become Mn2 plus. And Mn2 plus has a very light pink color, but due to the concentration of Mn2 plus that we have here, the solutions appear to be colorless. Keep in mind, your observations will be the purple color of acidified potassium permanganate becomes colorless when you react potassium permanganate with aromatic aldehydes or ketones. In this tube A, we had benzaldehyde. In this tube A, we had benzaldehyde. And initially, upon adding acidified potassium permanganate, this was the color of potassium permanganate. But after heating it up, it turned colorless. And in tube B, we had acetophenone. In tube B, we had acetophenone, and upon addition of acidified potassium permanganate, this was the color that the tube appeared. But after heating it for a while, we saw that the color of potassium permanganate disappeared because potassium permanganate got converted into, or permanganate ions got converted into Mn2 plus ions, which is almost colorless. When potassium permanganate is acidified, it acts as an oxidizing agent. When it is acting as an oxidizing agent, the aromatic aldehydes and aromatic ketones get converted to their carboxylic acid. When it comes to aliphatic aldehydes and aliphatic ketones, we saw the aliphatic aldehydes react well with acidified potassium permanganate, allowing it to get oxidized. So we can see here we have acetaldehyde that have gotten oxidized to acetic acid or ethanoic acid. And in doing so, potassium permanganate or the permanganate ions got converted into Mn2 plus, which were colorless. But aliphatic ketones do not show a reaction with acidified potassium permanganate. So therefore, we can come to the conclusion that with acidified potassium permanganate, aliphatic ketones cannot be oxidized. And the benzaldehyde we had over here got converted into benzoic acid. You can see a white color precipitate forming here because benzoic acid is insoluble in water, and you can see a tiny white color precipitate being formed here. So this fine benzoic acid precipitate appears to be a cloudy solution because these fine particles of benzoic acid is suspended in this area. Here again we can see a slight cloudiness of this mixture as well. What we have here is acetophenone after it has taken part in a reaction with acidified potassium permanganate. So acidified potassium permanganate was able to convert acetophenone, an aromatic ketone, into its carboxylic acid, which is benzoic acid. You can see again cloudiness here. That is due to the conversion of acetophenone into benzoic acid, which is insoluble in water, which results in formation of a white color precipitate due to being insoluble in water. In summary, students, when you are trying to react aldehydes and ketones with acidified potassium permanganate, the observations we had were aliphatic aldehydes will react with acidified potassium permanganate. Aliphatic ketones do not react with acidified potassium permanganate. Aromatic aldehydes and aromatic ketones both do react. Both of them do react with acidified potassium permanganate. That is a summary of the reactions that we see of the carbonyl compounds with acidified potassium permanganate. Let's move on to another oxidizing agent, that is acidified dichromate solution. In this part of our practical, we will see how acidified potassium dichromate, we can see this orange color solution here. We are going to see how aldehydes and ketones react with acidified potassium dichromate. Like in our previous examples, we will be taking a look at aliphatic carbonyl compounds and aromatic carbonyl compounds separately. We have acetaldehyde as our aliphatic aldehyde. We have 2-propanone as our aliphatic ketone. We have benzaldehyde as our aromatic aldehyde, and as our aromatic ketone, we have acetophenone. Right? So, first of all, let's start to add acidified potassium dichromate into our aliphatic aldehyde. So, we have our aliphatic aldehyde here, acetaldehyde, also known as ethanol. We'll take a test tube labeled A and place some acetaldehyde into this test tube. And now we will take our acidified potassium dichromate and add a small amount of acidified potassium dichromate into this. And let's observe what happens to the color of the solution. Upon addition of acidified potassium dichromate, you can see the color of the solution gradually starts to change. Earlier on, acidified potassium dichromate had an orange color. You can see while you wait, it turns into a green color. Now it is completely green. The solution is completely green now. The reason for this is that acidified potassium dichromate is also a good oxidizing agent. So it can oxidize the acetaldehyde into acetic acid, or in other words, ethanol will be oxidized into ethanoic acid. So when this is happening, the dichromate ions present in the medium are the responsible species for this orange color in the dichromate solution. So the orange color dichromate ion converts into chromium ions, or Cr3 plus ions. As we have seen earlier, chromium ions are green in color. A chromium ion solution is going to be green in color. That is why you observe a green color in this medium. Let's add a little bit more to see a very clear green color. Now you can see as soon as I add a little bit of acidified potassium dichromate, it turns into orange again, and gradually you can see the orange color turns to a green color. Now it is green in color. This is due to the formation of chromium 3 plus aqueous ion solution. We saw that aliphatic aldehyde reacts with acidified potassium dichromate. Let's move into our aliphatic ketone. We have 2-propanone, or in other words, we have acetone here. Let's take a small amount of acetone into our test tube labeled B. And to this acetone, we will add acidified potassium dichromate. Upon addition of acidified potassium dichromate, what are the observations you see? Do you see a color change? To observe this very closely, to another test tube, let's take a little bit of acidified potassium dichromate. Now, we can compare the colors of acidified potassium dichromate along with acetone treated with acidified potassium dichromate. So the color has not changed. Only thing that you see here is a small dilution of the color. But to make sure that we are not seeing a color change, not because of how slow the reaction is happening, we are going to place both of these test tubes in a water bath. So if there's a very slow reaction happening in this test tube B, where we have our acetone mixed with acidified potassium dichromate, we want to make sure that we provide it with enough heat for the reaction to take place faster. But if there is no reaction taking place, you will see that this color persists without it changing color. We now place both our control and our reaction mixture in the water bath. We will let it stay there for a while. Students, now we have allowed the two test tubes to heat up in a water bath for a while now. Let's see what the observations are. Over here, we have the two test tubes. In test tube B, we have our acetone mixed with acidified potassium dichromate, and on my left hand, what I have here is just a sample of acidified potassium dichromate. Upon heating, both of them did not change color. So let's put aside the control and focus on our acetone containing test tube. So in the presence of acidified potassium dichromate, acetone did not have any reaction. That is why the color of the potassium dichromate persisted. Right? So this is an indication that aliphatic ketones do not react with acidified potassium dichromate. So there is no observation when you are reacting acidified potassium dichromate with aliphatic ketones. Now, let's move on to aromatic aldehydes and aromatic ketones. We have benzaldehyde as our aromatic aldehyde. We'll take a small amount of it into our test tube A. And into our test tube B, we will take our aromatic ketone, which is acetophenone. We will take a small amount of acetophenone and add it to our test tube B. And now, to both of these test tubes, let's add a small amount of acidified potassium dichromate to see if the color of acidified potassium dichromate will change into a green color like in the acetaldehyde reaction. So we have our potassium dichromate, acidified potassium dichromate solution over here. We'll add small amounts of it into both test tube A and test tube B. As you can see, upon addition of acidified potassium dichromate to both of these test tubes, we cannot necessarily see a color change. This could be due to the reactions happening very slowly. So what we are going to do is we are going to heat these test tubes up. After shaking each of these test tubes a while, I will be heating these two test tubes up to see if the color of these acidified potassium dichromate solutions will change over time. Let's place them both in a water bath and heat them up for a while. When we provide these two mixtures some heat, the reaction will happen faster, and then if there is going to be a color change, we will be able to observe it faster due to providing it heat. Let's see after a while whether the color has changed. Students, we have allowed the two test tubes to be heated in the water bath for a while now. Let's take them out. You can see here the two test tubes now have changed in color. Let's compare one by one. Initially, when we added acidified potassium dichromate, the acidified potassium dichromate had this orange color. So on this bottom layer, the color that we observed was this orange color. Now after a while, you can see when we added benzaldehyde and acidified potassium dichromate and mixed the two together, and we allowed it to react under elevated temperatures. So we heated this mixture up and we saw the reaction was happening a little bit faster than at room temperature, and the potassium dichromate color, or the dichromate ions color, the orange color, disappeared and it turned into a green color. And at the same time, there's a little bit of a cloudy nature. That is due to the fact that benzaldehyde got oxidized to benzoic acid, which is a white color precipitate because it is not soluble in water. So the white color precipitate that you see here over on the top layer, as well as you can't necessarily see the white color precipitate here on the bottom layer. However, we have formed a white color precipitate, which is benzoic acid, insoluble in water, as well as the dichromate ion has converted into chromium 3+ ion. So the dichromate ion has actually reduced, whereas the benzaldehyde has oxidized into benzoic acid. Now let's see what happened to acetophenone when it was reacted with acidified potassium dichromate. You can see here, when acetophenone was reacted with potassium dichromate, the color of the dichromate ions have turned to a green color. Dichromate ions are orange in color. Due to dichromate ions reducing to chromium 3+, we can see a green color solution being formed here. And over here, we can see a precipitate being formed. Acetophenone, when oxidized in the presence of acidified potassium dichromate, it will convert into benzoic acid. Benzoic acid is insoluble in water. That is why you can see a cloudy nature in this green color solution as well. And over here, we can see a white color precipitate formed, that is benzoic acid, insoluble in water. Now, let's take a look at our summary. Initially, we reacted acetaldehyde with potassium dichromate, and we can see in the presence of acidified potassium dichromate, acetaldehyde got oxidized into acetic acid. So in this oxidation, the dichromate ion got reduced to chromium 3+. So what you see here is the color of the chromium 3+ aqueous ions that are present in the medium. So it is green in color as chromium 3+ aqueous ions are green in color. So in the presence of acidified potassium dichromate, acetaldehyde gets oxidized into acetic acid. And then we took another aliphatic ketone, which is acetone or 2-propanone. In the presence of acidified potassium dichromate, acetone did not show any reaction. Acetone did not react with acidified potassium dichromate, so therefore there was no color change. We can still see the color of acidified potassium dichromate persisting in that test tube. And to benzaldehyde, when we added acidified potassium dichromate and heated it, we got a mixture of two layers. You can see in the aqueous layer, the color of potassium dichromate has changed from orange to green. This is due to the dichromate ion reducing to chromium 3+ while oxidizing the benzaldehyde into benzoic acid. So the cloudiness is due to the white color precipitate that is formed, benzoic acid, which is insoluble in water. When we reacted acetophenone with acidified potassium dichromate, we saw the same observation. The aqueous layer, which was orange in color due to the presence of acidified potassium dichromate, got converted into a different color, which is green, due to dichromate ions reducing into chromium 3+ ions. And while this reduction is happening, the acetophenone got oxidized into benzoic acid. And again, due to benzoic acid being insoluble in water, you can see white color precipitate present here and of benzoic acid. With that, we come to an end of the reactions that you see with acidified potassium dichromate with aldehydes and ketones. Now, we plan to move on to our next test, which is the reactions that you see with tolerance reagent. So aldehydes and ketones, how they react with the tolerance reagent can now be tested. In this section of our practical, we will focus on how these aldehydes and ketones react with the tolerance reagent. So what we have here is our tolerance reagent. The way that we can prepare this is mentioned in our practical book as well. But just to go over the method, again I will mention it here. We will take silver nitrate solution, and to it we will add a few drops of sodium hydroxide. Upon addition of sodium hydroxide, you will see a precipitate being formed, and to that precipitate you have to keep adding ammonia until that precipitate dissolves. The resultant solution is referred to as ammoniacal silver nitrate. Another name for that is tolerance reagent. So what we have here is our tolerance reagent. So just like in the previous experiments, we will take our aliphatic aldehyde and aliphatic ketone and add tolerance reagent and see what happens. So I will take aliphatic aldehyde, which is ethanol or acetaldehyde. Now I have a test tube labeled A here. To that test tube, I will take a small amount of ethanol. Now you can see I have taken a small amount of ethanol here. To that, I will add tolerance reagent. This reaction is very slow and will not take place clearly at room temperature. So we will have to heat it up. But first, let's set it aside for a while. And we'll take another test tube labeled B, and to this we will add our aliphatic ketone. And to our aliphatic ketone, we'll add small amount of tolerance reagent as well. And now, in our test tube A, we have our aldehyde, which is acetaldehyde, mixed with our tolerance reagent. In our test tube B, we have our ketone, aliphatic ketone, acetone, mixed with tolerance reagent. Let's place them both in a water bath and leave it there for a while to see if they answer to the tolerance reagent. While they warm up, I will explain to you what happens here. When you add tolerance reagent onto aldehydes, aldehydes get oxidized into carboxylic acids, and tolerance reagent have silver ions that gets reduced into silver solid. So this silver solid that is formed gets coated on the interior walls of the test tube, and the test tube appears to be a silver mirror. Due to deposition of silver solid on the interior walls of the test tube is going to appear as a silver mirror. So we will leave test tubes for a while. We know in the test tube B, we are having a ketone. Ketones do not answer to the tolerance reagent, so you will not see a silver mirror being formed with ketones. However, test tube A should end up forming a silver mirror as we have an aldehyde in the test tube along with our tolerance reagent. When we heat it up for a duration, we should get the result of seeing a silver mirror. Students, we have allowed the two test tubes to heat up for a small duration, right? So after about 5 minutes, now we are going to observe the changes of the two test tubes. So let's take the two test tubes. You can see here the test tube A. The test tube A has formed a silver mirror, but the contents in test tube B have not formed a silver mirror. So contents in test tube B has not formed a silver mirror because we had a ketone in there. Ketones do not answer to our tolerance reagent test. So let me show you the silver mirror that is formed very clearly. Let me remove the contents of this test tube into another beaker. And now we can very clearly see the silver mirror that is formed when we reacted an aldehyde, aliphatic aldehyde, with the tolerance reagent. So what you see here is a silver mirror that is formed when acetaldehyde or ethanol was reacted with the tolerance reagent and was heated up for a while. You can see the interior walls, the entire interior walls of this test tube is now coated with silver, and the test tube appears to be a silver mirror. So this is the silver mirror test. This is a positive answer to the silver mirror test. And over here in the test tube B, what you see is a negative answer, which means it does not answer to the silver mirror test. So ketones do not answer to the silver mirror test. Now let's move on to the second set of experiments here, that is the reaction of aromatic aldehydes and aromatic ketones with tolerance reagent. So, like in the first experiment here, let's add our aromatic aldehyde that we have here, benzaldehyde, into our test tube A. We will take a generous amount of the aldehyde to make sure that we see a really good silver mirror when it is formed. So, we have taken benzaldehyde into test tube A, and into our test tube B, let's add acetophenone, our aromatic ketone. We will take small amount of acetophenone into this test tube, and we will place it here. So, in our test tube A, we have benzaldehyde, and in our test tube B, we have acetophenone. Now, to both of those test tubes, let's add our tolerance reagent. We have added our tolerance reagent here. Into test tube B as well, we will add our tolerance reagent. As you can see, now we have added to both the test tube the tolerance reagent, and to test tube A we have added our aromatic aldehyde, and in test tube B we have our aromatic ketone. Now, we will place them in a water bath for the reaction to go to completion. We will leave it there for a while and come back and take a look at the observations. Students, we are here after a few minutes to observe the changes that has taken place when we place the two tubes on a water bath. So, let's take tube A and tube B out of the water bath. You can see here tube A and tube B are different now. As you can see, tube A has formed a silver mirror, but tube B has not formed a silver mirror. As you can see, the test tube A containing the aromatic aldehyde has answered positively to our silver mirror test, forming a silver mirror inside the test tube. And the aromatic ketone containing tube B, test tube B, has not answered positively to the silver mirror test. So, we will set it aside for a while and let me remove the contents of this test tube. Now, you can very clearly see how the interior walls of the test tube A is coated with silver. Again, as I mentioned before, when we carry out the silver mirror test with the help of tolerance reagent, the silver plus ions in the tolerance reagent gets converted into silver solid. While this reduction is taking place, the aldehyde that was present inside this mixture gets converted into a carboxylic acid. So, the aromatic aldehyde we had, which is benzaldehyde, gets converted into benzoic acid, and silver plus ions got converted into silver solid, and this silver solid got deposited onto the interior walls of this test tube, creating a silver mirror. Let's move on to the summary of this experiment. In this experiment, we looked at aliphatic aldehyde which answered positively to the tolerance reagent test, forming a silver mirror. Aliphatic ketones did not answer positively to our silver mirror test with tolerance reagent. And then we took a look at aromatic aldehyde. Aromatic aldehyde gave a positive result for our tolerance reagent test, forming a silver mirror, as you can see here. Aromatic ketones did not answer positively to our silver mirror test. So in conclusion, we can see all the aldehydes, regardless of whether it is an aromatic aldehyde or an aliphatic aldehyde, it will answer positively to our silver mirror test. Ketones will answer negatively. It will not provide you a silver mirror when you react a ketone with tolerance reagent. With that, let's move on to the final section of this practical, which is the reaction of aldehydes and ketones with Fehling's solution. In this final part of our practical, we will be taking a look at how aldehydes and ketones react with Fehling's solution. Here we have our Fehling's solution. This Fehling's solution is prepared by mixing equal amounts of Fehling's A and Fehling's B. So we have two solutions that are named Fehling's A and Fehling's B. We mix equal quantities of these two solutions and prepare our final Fehling solution. Fehling's A contain copper 2 sulfate or copper sulfate, CuSO4. So that is why Fehling's A solution is going to be a blue color. And then we have Fehling's B made with potassium sodium tartarate. So when you mix the two up, we get our final Fehling solution, which we have here. Fehling solution will react with aldehydes, especially aliphatic aldehydes, and form a brick red color precipitate. However, Fehling solutions do not react with ketones, and also it does not react with any aromatic aldehydes. So it only answers to aliphatic aldehydes. Aliphatic ketones, aromatic ketones, and aromatic aldehydes will not answer to our Fehling's test here. So let's move on and see if we can notice these observations. When we are doing this experiment, we will have to use a boiling tube, and we will be adding our Fehling's solution to each of these aldehydes and ketones we have in front of us, and we will be heating it up with the help of a Bunsen burner. So since we are going to heat it up with the help of a Bunsen burner, I'll be using this test tube holder to make sure that heat does not transfer to my fingers while holding a boiling tube. Let's take our aliphatic aldehyde ethanol into our boiling tube. So we have ethanol or acetaldehyde, the common name for ethanol. We will add a small amount of ethanol into our boiling tube. And now we will take our Fehling's solution and add a small amount of Fehling's solution into this boiling tube. So as you can see, upon addition of Fehling's solution into this boiling tube, when it is added with ethanol, the resultant solution is still blue in color. The reason for this is this reaction is happening very slowly, so we will have to provide heat for this reaction to take place. So now let's heat this boiling tube. When you are heating a solution like this, please make sure to aim the opening of the boiling tube away from you. If any spilling or splashing is to occur, at that point, you make sure you are safe by aiming the boiling tube away from you. Now you can see when I heat it up, gradually the color of this solution changes little by little, and we are hoping to obtain a brick red color precipitate. Already it shows a slight orange color. If we heat it long enough, it will finally produce the brick red color precipitate that is characteristic of this failings test. Students, you can observe here the formation of a brick red precipitate. Over here, although it appears as if it is a solution, what you see here is a formation of a brick red color precipitate. So what happens here is, in the initial solution of failings, we had copper 2+ ions, and when it is reacting with the aldehyde, aldehyde oxidizes to a carboxylic acid. So we had ethanol, it oxidized to ethanoic acid. So what happens here is copper 2+ ions got reduced to copper 1+ and formed cuprous oxide, Cu2O, cuprous oxide, or copper 1 oxide. So what you see here as a precipitate is a brick red color cuprous oxide. Let's move on to the next experiment. Now we will take an aliphatic ketone, which is acetone. We have acetone as our aliphatic ketone, and we will react it with failings solution. We already know that the failings solution will not answer to aliphatic ketones or aromatic ketones for that matter. It will not answer to aromatic aldehydes as well. So the only positive test we are going to see for the rest of this experiment is going to be our aliphatic aldehyde that we saw earlier. But still, let's go on with our experiment and see if there's any color change that we can observe. Now let's heat the reaction mixture containing our aliphatic ketone and the failing solution. As you can see, upon heating it, we are not seeing any change. This is because the ketones cannot oxidize into carboxylic acids. Aliphatic ketones cannot oxidize into carboxylic acids in the presence of an oxidizing agent like failings solution. So we can see the solution is starting to boil, but still no color change. This indicates that in the presence of failing solution, aliphatic ketones do not have a reaction. Aliphatic ketones cannot convert into carboxylic acids with the help of failing solution, so therefore no reaction will take place. We will now safely remove this into our test tube rack. And we will move on to our next experiment, which is reacting failing solution with an aromatic aldehyde. Now we have our aromatic aldehyde, benzaldehyde. Let's take benzaldehyde and see what happens when we add failings. We'll take a small amount of benzaldehyde into a boiling tube. And to that, we will add a small amount of Fehling's reagent. We'll mix it together as much as we possibly can. And let's observe if there's going to be a color change when you heat this solution up. So now, as you can see, benzaldehyde is not soluble in water, and Fehling's solution is mostly organic, and Fehling's solution is mostly aqueous. So you can see there's somewhat of a layer separation there. When you heat it, as in the previous experiment with the ketone, the aromatic aldehyde also does not show a color change. As you can see, it boils off, sometimes shoots out as well, so you have to be very careful pointing it away from you. And when you're pointing these things away from you, please make sure not to point it at anyone else as well. Because when this boils off, it might splash out of the opening of the boiling tube, which might result in a burn injury in someone in front of you. So as you can see, upon heating it until some of the organic layer boils off, we saw no color change. Still, the blue color of the Fehling's solution persists. This is an indication that aromatic aldehyde did not have any reaction with the Fehling's solution. If the Fehling's solution reacted with it, it will end up forming copper 1 oxide or cuprous oxide, which is a brick red color precipitate. We did not see that here, indicating that the Fehling's solution did not react with the aromatic aldehyde we had here, benzaldehyde. Let's move on to the aromatic ketone. The aromatic ketone we have is acetophenone. We have acetophenone here. Let's take a small amount of acetophenone onto our boiling tube. And to acetophenone, let's add a small amount of Fehling's solution. Again, as you can see, there will be layer separation because acetophenone will not dissolve in Fehling's solution, which is mostly aqueous, and acetophenol is an organic nonpolar layer which will not dissolve in the Fehling's solution. But we will mix it up as best we can. And then we'll heat it up with the help of a Bunsen burner. If there is any reaction, we will see a color change in the Fehling's solution layer. When you are heating it up, please be very careful. These are all organic solvents. They will quickly evaporate as well as quickly boil off. It could result in a splash hazard. So you can see the organic layer, although it's boiling, still there is no color change. Still there is no color change, indicating that the Fehling's solution was not capable of oxidizing the aromatic ketone. So the aromatic ketone did not get oxidized into a carboxylic acid. So therefore, the Fehling's solution retained its color that comes from copper 2+ ions. So having this blue color indicates that in the presence of Fehling's solution, aromatic ketones, in this case we specifically took acetophenone, acetophenone does not react with the Fehling's solution. Students, let's move on to our summary, and this is our final experiment in the experiment number 27 practical series. So in this final step, we observed that with Fehling's solution, only aliphatic aldehydes give positive results and form brick red color precipitate. Only aliphatic aldehydes will form brick red color precipitate in the presence of Fehling's solution. Aliphatic ketones did not change the color of the Fehling solution because aliphatic ketones cannot get oxidized in the presence of Fehling's solution. So you can see the blue color of the Fehling solution actually persisted upon heating as well. Then we took benzaldehyde, our aromatic aldehyde. Even that did not react with Fehling solution. The color of the Fehling solution did not disappear due to Fehling solution not reacting with aromatic aldehydes. Finally, we looked at aromatic ketones. Even that did not turn the color of the Fehling solution into a brick red color, indicating it did not react with the aromatic ketones as well. So only aliphatic aldehydes answer to Fehling solution. Aromatic ketones, aromatic aldehydes, and aliphatic ketones do not answer to Fehling's solution. With that, we finish the practical number 27, and now let's move on to important theory parts related to this practical as well as some questions related to this practical.